I just did several videos on the binomial theorem, so I think and now that they're done, I think now is a good time to do the proof of the derivative of the general form. So let's take the derivative of x to the n. And now that we know the binomial theorem, we have the tools to do it. So how do we take the derivative? Well, what's the classic definition of the derivative? It is the limit as delta x approaches 0 of f of x plus delta x, right? So f of x plus delta x in this situation is x plus delta x to the nth power, right? Minus f of x, well, f of x here is just x to the n. All of that over delta x. And now that we know the binomial theorem, we can figure out what the expansion of x plus delta x is to the nth power. And if you don't know the binomial theorem, go to my pre-calculus playlist and watch the videos on the binomial theorem. So the binomial theorem tells us that this is equal to, and I'm going to need some space for this one, the limit as delta x approaches 0. And what's the binomial theorem tell us? This is going to be equal to, I'm just going to do the numerator, x to the n plus n choose 1. And once again, review the binomial theorem if this looks like Latin to you and you don't know Latin. N choose 1 of x to the n minus 1 delta x plus n choose 2 x to the n minus 2, that's x to n minus 2, delta x squared, right? Delta x squared, and then plus, and we have a bunch of digits. And in this proof, it actually, we don't have to go through all the digits, but the binomial theorem tells us what they are. And of course, the last digit, we just keep adding, is going to be 1. Well, it would be n choose n, which is 1. Let me just write that down. N choose n. And it's going to be x to the 0 times delta x to the n, right? So that's the binomial expansion. And let me switch back to minus. So all of that's green, that's x plus delta x to the n. So minus x to the n, minus x to the n power. That's x to the n. I know I squunched it there. All of that over delta x. Let's see if we can simplify. So first of all, we have an x to the n here, and at the very end, we subtract out an x to the n. So these two cancel out, right? And then if we look at every term here, every term in the numerator has a delta x, right? So we can divide the numerator and the denominator essentially by delta x, right? This is the same thing as 1 over delta x times this whole thing. So that is equal to, the limit as delta x approaches 0 of, so we divide the top and the bottom by delta x, or we multiply the numerator times 1 over delta x. We get n choose 1 x to the n minus 1. What's delta x divided by delta x? Well, that's just 1, right? Plus n choose 2 x to the n minus 2. This is delta x squared, but when we divide by delta x, we just get a delta x here, delta x. And then we have we keep having a bunch of terms. We're going to divide all of them by delta x, right? And then the last term is delta x to the n. But now we're going to divide that by delta x. So the last term becomes n choose n. N choose n. X to the 0 is 1, so we can ignore that. Delta x to the n divided by delta x. Well, that's delta x to the n minus 1, right? And then what are we doing now? Well, remember, we're taking the limit as delta x approaches 0. So as delta x approaches 0, pretty much every term that has a delta x in it, it becomes 0, right? We just, when you multiply by 0, you get 0. So every term, this first term has no delta x in it, but every other term does. Every other term, even after we divide it by delta x, has a delta x in it. So that's 0. Every term is 0. All of the other, I don't know, what is it, n minus 1 terms? They're all 0. So all we're left with is that this is equal to n choose 1 of x to the n minus 1. And what's n choose 1? That equals n factorial over 1 factorial divided by n minus 1 factorial times x to the n minus 1. 1 factorial is 1. And if I have 7 factorial divided by 6 factorial, that's just 7. Or if I have 3 factorial divided by 2 factorial, that's just 3. You can work it out. 10 factorial divided by 9 factorial, that's 10. So n factorial divided by n minus 1 factorial, that's just equal to n. So this is equal to n times x to the n minus 1. So that's the derivative of x to the n times x to the n minus 1. So we just proved the derivative for any positive integer when x to the power n, where n is any positive integer. And we see later it actually works for all actually real numbers in the exponent. So I will see you in a future video. See ya. Oh, and another thing I wanted to point out is, I said that we had to know the binomial theorem, but if you think about it, we really didn't even have to know the binomial theorem, because we knew, in any binomial expansion, I mean, you would have to know a little bit, but if you did a little experimentation, you would realize that whenever you expand, a plus b to the nth power, the first term is going to be a to the n, and then the second term is going to be plus n a to the n minus 1 b, right? And then you could keep having a bunch of terms. But these are the only terms that are relevant in this proof, because all the other terms get canceled out by, when delta x approaches 0. So if you just knew that, you could have done this, but it's much better to do it with the binomial theorem. Ignore what I just said if it confused you. I'm just saying that we could have just said, oh, there's the rest of these terms just all go to 0. Anyway, hopefully you found that fulfilling. I will see you in future videos.